So welcome to this pre-recording of a lecture on symbolic computation, or rather on making what looks like graphical user interfaces from within computer algebra systems such as SageMath. So the title is on making interacts. So we have seen in this course how to make animations. With an animation, everything is fixed in advance. Also, the speed, the pace of the animation, we can fix this once, but then it runs and we can just watch it play out. With an interact, we can give control to the user. So here is an example. We have seen this example already, the tangent line to a curve problem. Here the curve is given as an explicit equation, y equals f of x. And we can, so here you see in blue the curve, in red there is the point on the curve, and then there is the tangent line. Now what you can see is that there is a slider on top, and with the slider one can slide the point from left to right, from right to left. And as we do this, the tangent line is going to be recomputed and redrawn. So normally if we had to compute everything from scratch, then this would be quite an involved application. We will see that there are only a certain number of directives that need to be added. The most important step is always the first step. What is it that you want to export? What is the parameter that drives the interaction? So in the previous example on the tangent line, this was the x-coordinate. Once you have that, one can then put that parameter as the argument of a slider. Other elements of similar to the design of graphical user interfaces, you can have a selector, you can also have a drop-down menu. It doesn't end there, so you can deploy the interact on an HTML page. That HTML page then will connect to SageMath. So for that then to work, one needs to run what needs to be connected to the internet. And I have a web page open, and I hope to be able to demonstrate this. Tangent line is perhaps not that interesting, but here is an application from mechanism design. This is a schematic of a 4-bar mechanism. And this is a famous 4-bar mechanism. It translates vertical or linear motion to circular motion, attributed to Chebyshev. So what happens is that we see this the opposite way. So this mechanism has also other applications. One can imagine here a wheel turning, and the parameter that controls this mechanism is an angle. So it's the angle of what one calls the crank. And as this crank turns, the bars, they are rigid, so they do not stretch or bend. So they make this connector point move, and then we have the coupler point. For these specific dimensions that we will have here, the red point will trace what looks like a horizontal line. And actually it's a part of a curve of degree 6. And computing the coordinates of the connector point can be done with solving a system of polynomial equations. So in a sense, this is an application also of the previous part. So the connector point, the point that is connected to the endpoint of the mechanism, and it's also connected to the crank. So the conditions that express that the bars remain rigid can be translated into two circles. So essentially we are going to intersect two circles given here in symbolic form. We have the same length of the bars, so there are different bars. Perhaps I should flip back. So there is this green bar here, and then there is the red bar. So the first circle is easiest. So the first circle has center 2, 0, and we are after the coordinates x and y for this connector point. So this is the central point in this mechanism. And here is the equation for that circle. The circle that expresses that this point with coordinates x and y is at distance 5/2 from 2, 0. Then we had the green bar, and we have the end point of the crank. So the theta is the angle that drives the mechanism. But we can translate this into an algebraic system by abbreviating the sine and the cosine by c and s. And then we have the second equation also for a circle. So the coordinates of the connector point are thus the intersection of these two circles with two parameters. And the two parameters c and s are the algebraic parameters. There's only one angle there that drives the whole mechanism. Okay, we will see how we can compute these coordinates with the elimination of the variable. So we can express x and y as polynomials in the, or as probably not polynomials, but as expressions. We can find explicit expressions for the coordinate x and y in terms of c and s. It will turn out to be solving a quadratic equation. Okay, so these are the slides. I have two browsers open. Perhaps I should flip first to the first browser. So this is the browser with the Interact, for which I need the connection to the internet. So perhaps I will need 2 attempts. Here is the web page, and it works immediately. So I'm running this from a separate browser. I have not deployed the web page. Browsers also can work as file browsers. So you see that here in this window I have the name of the file. And how does this now work? When I'm clicking on this interact, I can move the tangent line. So here you see that I can walk from step to step, and you see each time the point and the tangent line, they move. So I'm using the Firefox browser. Firefox has the advantage that you can see the page source from, so there's this tools button, and here is the page source. So there is some template code. And you can actually see the links to the Sage cell. So at the very beginning of this course, when you want to use Sage without logging in, just by doing a simple calculation, well, in some sense, it is still a simple calculation for Sage. We can send this code to Sage, and Sage will evaluate this script. So this is some raw HTML that is placed within a script element. And I will also show the code in the Jupyter notebook. So then there is the other application, which is more involved. So here you see the angle. The angle is now at close to pi over, a little bit more than pi over 2. So let me move that angle more. So then you see that the mechanism also moves. So I have a slider that controls the angle of the crank. And here you see that we are almost making one full turn. So the angle, the range of the angle goes from 0 to 2 pi. So we can go all the way back. So here we have one turn of the crank. Also here, this is one single function, and here you see the formulas for the explicit formulas, which involve the square root of the quadratic formula, the explicit formulas for the coordinates. And there is one single function. You see the keyword interact. So the single function is still a little bit more involved and more complicated, but it almost fits within one window. So as an animation, it's already, as a graphic, it's quite interesting, but the code that is necessary is still compact enough to be executed. All right. So that went well. So let me now go to the other browser with the Jupyter notebook. I will not go through this, so this notebook will be posted on the website, on the course website. I will go through this not by just typing it in, as I mostly do, because it's rather too involved and it would be just copying and pasting. At the beginning of this course, at the first lecture, I mentioned this book, the textbook by Gregory Bart. So I took what I know from interactive web pages I got from this book. And this is the first example is what I'm going to show, comes from this book. So we have an explicit curve. So here is the curve defined. So it's a cubic curve. You could have guessed this from the shape. And here is the plot. So I will go through this step by step. So at first, of course, one needs to know the plotting primitives. And one needs to do the computations. So I'm running this function. So let me describe what this function does. There are two global variables, so these are the functions fx and df. Df gives the derivative. There's one parameter, the x-coordinate for the coordinate of the tangent point. What happens is that we compute the corresponding y value by evaluating the cubic at the x-coordinate. Then we compute the derivative, and that will give the slope. So we have the slope, then we still have to compute the intercept. I documented this, so if you remember the equation of a line through a point, so the point is x naught, y naught, we have y minus y naught equals the slope times x minus x naught, or equivalently, slope is rise over run. Then I'm using this to compute, to justify the formula for the intercept. So that's the computation part. And then the computation continues by calling the plotting primitives. So we have to define the range, the grid lines are plotted, and then also the colors of the curve, of the tangent line, and of the point on curve. So that is the preparation work, and once this works, you can run this function for a couple of values of the coordinates. So here I'm running this for 0.5, here another value. So that is the foremost important step, and this goes back to what we did with two-dimensional plotting in the course. We are creating functions that give us that compute plots. So by the way, this would also be a good strategy to compute the frames in an animation. So as a side way, so one can also use these functions now to build the frames that are used in an animation. So instead of showing the plot, then the plot would be returned and stored in a list. So these functions are rendering the plots as well. All right, so this was the preparation work. And now there comes the copying and the pasting, and the adding of the keyword interact. And then you see here the slider. So let me run this function. See, the function evaluates immediately. So what are the coordinates? So we have the interact decorator. The x naught is now extended with this slider function. So the slider defines the range of the x naught between -2 and 2. It starts at minus 1.5. So you can see where it starts at minus 1.5. The label for the slider is the x-coordinate. And then there's one parameter, that's the 0.1, that is the step size. So each time when I move, the granularity of the step is just 0.1. So this determines how fine I can move. So you can see that each time I have a fixed granularity, and okay, so this is essentially it. So the slider is a very important element. We can also add a selector. For example, if you should wish to change the color of the function of the curve. So there is the RGB. So I can turn this in red, green, or blue. Or if you want, you can provide more colors. So what this selector does, so there is a label, and then the label, the list within the selector gives the options, gives the names of the available colors. So here the red, the green, and the blue. Another element, or did I skip something? So there is the selector. I thought, no, so this is, these are the two elements that I wanted to show. Okay, this is half of the lecture. Let me show the application now. So the application is the Chebyshev 4-bar mechanism, and the interact can be defined quite immediately. So we have the turning of the crank, which is defined by an angle ranging from 0 to 2 pi. We have the beginning, so which is pi over 20, and then the increment pi over 10. Okay, so let me run this. So each time when I move, you can see that the crank turns counterclockwise, and there is some delay. Also, it's actually an oval that gets, so I can make this now go in the opposite direction, clockwise, and you see that there is a delay. So it looks a little bit now like an animation. I haven't changed the aspect ratio, so then it would look like a circle. So using the polar representation of the coordinates, so the cosine and the sine, there are the primitives points. So there is the center, the endpoint. These are defined here, and then there is the line primitive, which takes on input a list of points. The plots are added together, and then it is important to define the range. So in the show, we've seen this also with the animations, one must provide the frame window. Otherwise, adaptively, you would see the coordinate system that moves, and the point would remain centered, or at least the line segment would be at the center of the plot. Okay, let's now go through the algebraic part. So this brings us back then to the solving of the equations. I will model the two circles within the polynomial ring. So there are then singular polynomials. Here I did this with the resultants, but you can see that the order is lexicographic. So I could go to the ideal representation and then ask for a Gröbner basis. These two steps would also give me the triangular form. I give the alternative here with resultants. So we eliminate x. So there are the two polynomials p and q. We apply the resultant method to one polynomial with the argument the other polynomial and then the variable that we want to eliminate. So you see that the result, it looks like a longer expression. So this all works if you do this a couple of times. Don't do this many times because you have expressions well. But here it actually, we only do the resultant calculations once, or actually once for x, once for y. By elimination, we can eliminate x and then we can eliminate y. So we have two expressions where we can express y in function of the two parameters, the c and the s. If you look a little bit closer to these expressions, observe that the degree in y is only 2. So this is the quadratic equation that we are seeing here. So that's the reason why the symbolic approach actually works so well here. So the other parameters, they appear of the power 4, but in some sense they are harmless. Okay, so once we have the resultants, we solve them. So going back to the symbolic ring, there are still issues that may happen. You see the square root. So if the square root would be negative, then that would result in things that we couldn't visualize so directly, or that wouldn't be in this application so useful. But here we are lucky. So this is the second time that we are lucky. We're lucky with the resultants. They turn out to be quadratics and not polynomials of degree higher than 2. So the solve can be done completely symbolically. And also the expressions, so the cosine and the sine here, we will be lucky in the sense that they will not be negative. So I'm selecting, also we have two solutions, and there is some trial and error here. So I did my preparation for this. So again, if I would do everything by hand in this lecture, it would take me more than the 40 minutes that I will use here. I was also going to say that regarding the arguments of the square root, why are they not negative? Well, one should try this. One should make a plot with the parameter of the angle and actually run it. And then one will see that these functions are not negative for the sines and the cosines, which are between -1 and 1. Okay, so I'm building up this interact step by step. So we first had the crank, so there is the sine and the cosine. Here now I'm extracting the coordinates of the angle, assigning them to the C and the S. The formulas are converted into functions. Within the context of this notebook, so I have evaluated, I hope everything, so let me, no, I have not, I just scrolled through, so let me evaluate to make sure that everything is fine. So within the context here of this notebook, the expressions are for the coordinate values, so they're stored in xv and yv. I'm turning this into functions of the cosine and the sine. So here I made it very explicit by using other letters. So the formal parameters of these two functions, so fx and fy, are functions in the sines and the cosine. And you can see where they are used. They are used to compute the coordinates of the crank. So the x and the y here give me, so these are the coordinates of the connector. So the coordinates of the crank are the C and the S. So let me indicate where they are. So the connector is this point over here. So this is the point. The connector point connects the bar that starts at 2, 0 So here you see the bar 2 to 0 to the connector point. The green line here, what is drawn in green, is the other bar that connects the endpoint of the crank to the connector point. So you can read the codes for the lines, how they are drawn. So this is a 4-bar mechanism. I didn't really explicitly say that, but we have these 3 bars, and then there is the bar that connects, that's not drawn here, but you see the coordinate axis between 0 and 2. Alright, and I should make the point that this works, so I can move that angle turning the crank, and there is some delay in running this animation. So when I move the angle, it goes counterclockwise, and I said that the bars do not deform, but I have actually not adjusted the aspect ratio, so it actually looks as if the bar actually of the crank is larger, but it traces out an oval, not really a circle. So I did not change the aspect ratio. So the angle moves counterclockwise, so it's from 0 to 2 pi. So this is a computationally intensive process, because the formulas are still interpreted, even if we have them explicit. So to make this more efficient, one would need to use Cython to add types to the and one would use, we actually are computing a lot of square roots. One would add, so this would make the course almost full circle. We go back then to the first part of the course, but for our practical purposes, this is efficient enough. Okay, so now the last interact. So, and I do not need 10 minutes for this. So everything fits within this one window. So it is complicated, but not as complicated that it would require extensive amounts of code. So this is kind of showing off the power of the modeling power. We can focus on what we now want to show. I want to add the coupler to this. So there is an extra bar that comes in, I call it bar 4, and that's the bar that connects the connector point to the coupler. So the line is computed, and here you see how this goes. The direction of the bar from the coupler, from the connector to the coupler, is in the same direction of the green bar. So we are adding this blue bar here, and this is actually one single bar, but it's drawn in 2 pieces. So what I'm going to do is I'm going to compute the vector that starts at the connector point and that ends at the crank, and then I'm going to add this vector, flip the sign, and add this up. So let's see if that is what I did. So I'm computing essentially the vector that starts at the crank, the coordinates c and s, so you have the dx and the dy, so these are the displacements in x and y. So one can now imagine the arrow, and since I'm having the same length, I do not need to rescale. So to the coordinates of the connector point, I'm adding the difference the difference in x and y. So this is this vector from the endpoint of the crank to the connector. And then I'm putting the start of that vector at the connector, and it ends at a coupler point. Okay, so let me make the point that this works. So every time that I click on it, I move the mechanism a little bit farther. So here you see the angle 3 pi over 2. And here it ends at 2 pi. So there is a delay that sits there, but everything works as intended. Alright, to finish, let me point at the deployment. So the HTML code. So I'm flipping back to the web page. So here you see the same code in this window. So a lot of copying and pasting again. What is so now it is wrapped. Now it's very important that everything is self-contained. So here I'm defining the variables again. Also I'm copied and pasted the entire expression. So the entire expression for the coordinate values, the symbolic expressions for the coordinates of the connector point. And then the functions are defined as well. So in a way, working with Interact, you think of one parameter, but then there are the global parameters that are just typically just in front of the Interact, just in front of the function. So you see here where they are called. So that's the important part. Make sure that everything is self-contained. In the before the deployment, it's often good practice to put a reset right in front of here in the code cell in the Jupyter notebook. So you can really check that there's one code cell and this gets copied into an HTML element of the script type. So you do not need to have Sage installed for that. You see here at the header, so this is what they call templated or boilerplate code. So you don't need to remember this. So I copied this from the textbook of Gregory Barth, Sage for Undergraduates. So this is a very nice application of the Sage Cell Server. Again, we kind of make the connection with the very first lecture. If you do not want to make an account, if you do not want to install, well, you can still run SageMath from the Sage Cell Server. Okay, this took me about 40 minutes to explain. It took me a lot longer to prepare everything, and in the regular semester, so this is a preparation for the summer class, this was spread out over 2 lectures. So there is a lot of new stuff, or perhaps not so much new stuff, but a lot of the novelty in this lecture is that we combine so many aspects of the SageMath that we have covered in this course. So I hope this was interesting. Thank you for watching this.